Hello everyone, my name is Tanya and topic for my today's presentation is nested interval theorem and its role in Heine-Borel theorem. So first of all, consider the following diagram. Here I have drawn the intervals of the type Gn where these are closed interval from 2 minus 1 by n to 2 plus 1 by n where n belongs to naturals. So the question is to the audience, can you see which elements they are approaching or in particular what it sits inside the intersection of all the GNs? Okay, so we can clearly see that the element 2 sits inside all these GNs. And this is not a coincidence. We can make some key observations of the interval given. Here we can clearly observe that all the intervals here are closed and bounded. Also, Jn plus 1 is contained in Jn and length of each Jn is approaching to 0 as our n goes to 0. This presentation is nested interval theorem and it's okay, a bit glitch. So now, next, these are not, some coincidence. And if we make all these conditions satisfied, we are saying that we are getting a singleton element in the intersection of all the GNs. So now let's journalize it, and we all know this theorem, which is known as nested interval theorem. So it says if we have the closed and bounded intervals in real numbers such that Gn plus 1 is contained in Gn for all n in naturals and the length of Gn goes to 0 as n approaches infinity, then the intersection of all the Gns contains precisely only one point. So again, I have here written in a formal way the example that I have discussed earlier. I encourage all of you to write it. Also, I am not going into the proof of the nested interval theorem. I will encourage you to read it and write it, and also to check that the conditions in the statement of nested interval theorem are redundant or not. Actually, we can't drop other conditions in the nested interval theorem. So you should find out the counter examples that why we can't drop the conditions in the theorem. So now our next topic is compactness. So can anyone from the audience can tell me what they understand from the word compactness? Any vague idea? Okay, so let me begin. So compactness, in English compactness means, yeah, Venkat Krishnan had said intact. Okay, so it's like the vaguely we can understand is that it is the quality of being closed and packed together. It's something like we can pack it together. Like vaguely we can understand, we can pick up that thing and put it in a box. It's like that. It's like a vague idea. So now, uh, these are some definitions which from we can take the intuition from this vague idea of putting something in a box. So let we have K, a subset from reals, and omega be any collection of subset of reals. And omega is said to be an open cover of K if each member of omega is an open set and K is contained in the union of sets from the collection omega. So it essentially means K is covered by union of open sets from omega. It's essentially the same thing. We said it that we can enclose it in a box. So something is covering it. Similarly here, the open sets from omega are covering K. And now the definition of subcover. Omega naught is said to be a subcover with respect to open cover omega of K if K is the subset of open sets from omega naught. So now this means that we can have any subset omega naught of omega, and if K is covered by the union of open sets from omega naught, then omega naught is said to be a subcover with respect to open cover omega. And now our main definition, K is said to be compact if every open cover of K has a finite subcover. This means if you give me any open cover of K, if I am able to give you a finite subcover, this means that the set K is compact. So all these definitions are true in general metric spaces, but I am particularly focusing on real line. So now a few examples to understand the concept of compactness. So now my first question is this set 1, 2, 3 compact? You can to prove that the set is compact, what we need to do is if you give me any open cover, I should give you a finite subcover. That's essentially the thing we have to do. So if we say like if omega, I have written here omega, which is the collection of oi, where I is any arbitrary set, then which open cover can I take? So if we think a little bit, we can see that this set A is contained in the union of open sets from omega. Okay, so this essentially means there exists some O1, O2 and O3 belonging to omega such that 1 belongs to O1, 2 belongs to O2 and 3 belongs to O3. So here A is contained in union of OIs where I is from 1 to 3. So here I am able to find a finite subcover for the given open cover omega. So this means the set 1, 2, 3 is a compact set in real numbers. So now in the same manner we can generalize it. What we can generalize is that any finite set in reals is a compact set. The same reasoning applies to the proof of this claim. So I encourage all of you to please write the proof on your own and then check that if you have written it correctly. So now comes an interesting example. The set of real numbers is not a compact set. Okay, so what do we mean by saying that something is not compact? So the question is to the audience, what do we mean by saying a set is not compact? Anyone can raise hand and answer the negation. Okay, so clearly a set is compact when for any open cover we are able to find a finite subcover. So negation is clearly that there exists a open cover of the set K such that we are not able to find a finite subcover. So the same thing we are going to do in the case of reals. We are going to find a open cover of reals, but that open cover should not have a finite subcover. So let's begin. So here you can observe the real line and you can see if I take the intervals of the type minus n to m. Like you can see here, minus 1 to 1, minus 2 to 2, minus 3 to 3, up to so on. Then R will be contained in the union of these intervals, clearly. So now my omega will be all the union of these types of intervals. Okay, but my claim is that this open cover of real numbers doesn't have a finite subcover. So how do I prove that this open cover doesn't have a finite subcover? So I will assume that suppose this open cover of omega, which is union of intervals of the type minus n to n. So suppose this open cover has a finite subcover in real numbers. Okay, this means there are some finitely many ni's. Let me name them n1, n2 up to so on nk, such that reals are contained in union of that ni's. So now see from the diagram that if we pick up the maximum natural numbers from n1, n2 up to so on nk, then if we say that nk1 is the maximum one, then it will essentially contain all the intervals of the type minus ni to ni. That will imply that reals are contained in the interval minus nk to nk. It is contained, reals are contained in an open interval, but this implies that reals are bounded. But we all know that reals are not bounded. So this means this is a contradiction and what we have assumed is wrong. So omega, the open cover of real, what we have assumed is doesn't have a finite subcover. This means reals are not compact. So these were some illustrations to, like we can fully understand the concept of compactness. So now comes our main theorem, which is Heine-Borel theorem. So I am going to prove it in the case of real numbers. So let Jn, so the statement of Heine-Borel theorem essentially says that any closed and bounded interval in real numbers is a compact set. So it is, I have just written the same statement here. So let me read it once. Let J be the interval closed and bounded, and let J alpha be any family of open intervals such that J is contained in union of alpha J alpha. It essentially means this family is acting as an open cover for J. Then there exists a finite subset F of lambda such that J is contained in union of alpha from F J alpha. It means that for this open cover, we are able to find a finite subcover. This essentially means that this interval J is compact. So first I will give you the idea of the proof. In this proof, we will prove by the standard method of contradiction. First, we will suppose that the J alpha, the open cover we are given, doesn't have a finite subcover. And then we will apply the standard method of bisecting our interval. And then we will see some of the properties of the intervals we will pick. I will tell you these are some interesting property we will observe from each interval, and then we will see, we will apply our favorite theorem that I have discussed above, and we will get a contradiction. So our supposition will be wrong and we will reach the conclusion or the proof of the theorem. So let's begin. So first we will prove the theorem by the method of contradiction. So now let's assume that J is not contained in union of any finite number of J alphas from the given family. Okay, so now we will bisect our interval AB. So let's bisect into two equal halves. So my actually observe it. If we bisect our intervals into two equal parts, then at least one of the subintervals is not contained in the union of any finite number of J alphas. Means one of the subintervals must not have a finite subcover. Okay, why? Because if both the subintervals of AB have a finite subcover, then union of that finite subcover will act as a finite subcover for the whole J. But we have assumed that J doesn't have a finite subcover, so it will, contradict our assumption. So at least one of these should not have a finite subcover. So I have written here the same thing. So now, see, let me say that the interval J1 is satisfying the property that I have mentioned before, and let us call that interval log, because it is very, tedious to say it again and again that it doesn't have a finite subcover. So I name this interval which doesn't have a finite subcover as the log interval. As we have divided AB into two equal parts, so length of J1 is B minus A by 2. Okay, so again, now we will bisect our interval into again two equal parts. So we will bisect J1 into two equal parts again, and the interval possessing the property of not having a finite subcover is named J2, and it is R again a rogue interval. Yeah, so now we can inductively repeat the process. And now, can you anticipate what type of intervals we will get? I think it's clearly visible. We will get closed and bounded intervals. Length of the intervals goes to 0, and they are nested intervals, that is Jn plus 1 is contained in Gn. So now we can apply our favorite theorem. So here I've written the same thing. The subintervals we will get will satisfy all the properties in nested interval theorem. So by nested interval theorem, there is a unique point in the intersection of all the GNs. Let me name them as X. So now, as X belongs to all the GNs, and GNs are essentially the subintervals of J, so X belongs to the union, alpha belongs to lambda, J alpha. So it belongs to the union of open sets from the open cover we are given. So as it belongs to union, so there exists some lambda from uppercase lambda such that X belongs to J lambda. So it means that X is sitting inside one of the open intervals from the given family. So now, as J lambda is an open interval, so there exists an epsilon greater than 0 such that x minus epsilon to x plus epsilon is contained in J lambda. It is true by the definition of open set because x will be interior point of it, but you can say it in this way that if our J lambda looks like A lambda to B lambda, then we can take epsilon less than the minimum of these distances. Then essentially that x minus epsilon to x plus epsilon will be contained in the interval J lambda. So now we are approaching towards the end of the theorem. I think many of you can guess what we should do and how to achieve a contradiction. So now I will choose a n in naturals such that b minus a upon 2n is less than epsilon. Remember, this choice is, okay, sorry. So this choice is very crucial, and you can, if you are writing a proof, then you can leave this choice and you can begin with the next steps. You will find out that you can essentially choose this n later on, but we are writing a formal proof, so that's why I have written it in first way. So I have choose n in natural such that b minus a upon 2n is less than epsilon. So my claim is that Jn is contained in this open interval. So now let y be any arbitrary element in Jn. Since x also belongs to Jn because x is in intersection of all the Jns. So xy belongs to Jn. So the distance between x and y is essentially less than length of Gn, which is b minus a upon 2n. But this I have taken less than epsilon. This means that Jn is contained in the interval x minus epsilon to x plus epsilon. But this interval lies inside J lambda, which is one of the member of the open sets in the family. So this implies that Jn is contained in J lambda, which is a contradiction because the Jn was a rogue interval. It doesn't have a finite subcover. But this is implying that Jn has a finite subcover. So our assumption is wrong, and hence J is contained in union of there is a finite subcover for the given open cover, which implies our interval J, which is closed and bounded, is a compact set. So hence we have proved the, I like this theorem a lot. Heine-Borel theorem, every closed and bounded set in reals is compact. So now a few follow-ups. So what happens if we drop one of the conditions from the theorem? Like if I assume that I can drop boundedness, is the result still true or not? So the both the hypotheses are not redundant. If we drop boundedness, then it will create problem. As we have discussed in the case of real numbers, they are not compact. So this one is a counter for that. And if we assume that the interval is not closed, this again a problem will arise because the interval 1 comma 2 is not compact. It is not closed and it is not compact. So, not compact we can prove by saying that this open cover for 1 comma 2 doesn't have a finite subcover. I encourage all of you to find out why this open cover doesn't have a finite subcover. So the it comes to the end of my presentation, but I also want to say that converse of this theorem is also true, that any compact set in reals is also closed and bounded. I encourage all of you to find it out and prove it. Thank you so much. So this was all about my presentation.